Okay, hi everyone. I'm going to continue topic. It was week 4 and I finished on week 4. I started to read the first article. Well, today I think I'm going to refresh it because topic wasn't so easy for me. Yeah, it was theoretical part of linear regression. So let's try to read one more time. Yeah. Well, I have in mind some questions, so let's set one more Excel sheet. I think I will have much more questions here. Lots of theoretical things that I didn't get last time. So today's plan is to do 2 Pomodoros with ML course, then 2 Pomodoros with statistic course, and then again 2 Pomodoros on course. Okay, and yeah. So yeah, and maybe after that one, I will do conclude, maybe rising goals. I don't know. Yeah, I will I will try to look on my goals and maybe like analyze it. Maybe I did something wrong. Maybe I misunderstood some topics. I will update results that I have here. So yeah. Okay, so let's go to the topic. Yes, so one more time. So we have variable y, dependent variable, and we have vectors x, I think. Okay. So, and we have vector w. So yeah, it seems like vector x or vectors x is kind of factors that independent factors maybe, or dependent factors between each other. So which describe vector y, and we have vector w, so we can vector omega, I don't know, which like measure implementation of each components of vector x. So the more we have weight here, there's actually somewhere called it weights. Yeah, here. Okay, and yeah, and yeah. So okay, and our model could be described as well as with this formula. So vector y is equal to matrix x or vector x. Is it actually? Vector. Yeah, it could be vector. Yeah. Okay. Yeah, got it. So in order to write this formula shorter, we can use matrix. So multiplication of vector and matrix will give us like sum of some matrices, sum of some vectors. Okay. And we also add some noise, so some errors that could like that corresponds to different like mistakes that describes our like differentiation between errors and between real world and model world. I don't know. Doesn't matter. And comes on. So we have m features. Each of them has n vectors, or n, I don't know, and each of them has n n, I don't know, n components, something like that. Okay. We also write the expression for each observation. Yeah, okay. On restriction, I also apply the model. Otherwise, it will be another sort of regression bias. Okay. So let's try to understand what this, why we need this border. So one of the ways ordinarily. Okay, so try to visualize what it is. Okay, one more time. Have some kind of formula. So what it is? F So the board is kind of laggy, so I will refresh it. So okay, what we have again? So we have vector omega 0. Yes, vector. No, it's not vector. Okay, so maybe well, maybe it's a little bit easier. So we can describe our vector y as omega 0 plus some omega I xi, something like that. So what we have? We have I don't know, m like subjects, m features, and we can describe our vector with our number, our like variable, with this formula somehow. And after that, yeah, well, we can write it simply, like something like this vector w omega transpond and multiplied by a vector x, which has what? Which includes some like sample of each features. We have m features here, or m plus 1. We have m features, and I think first of them or last of them, I think, yeah, first of them, x0 is equal to it's fake fiction variable that we need only just for our formulas. Okay, so what? Okay, it's nice. And what we can do? We can like to observe more of these features. Like we can to do sample. Like we can do like n experiments, and we can create like x1 1 1 xm1, and we can create like n of them. So we will have matrix with size m plus 1. Okay, yeah, I got it. And n plus 1 columns and n strings. No. M plus 1 rows of strings and n columns. Yeah, I got it. Okay. And what next? Okay. Yeah. Okay. So we got our formula, and after that we add some noise to this to this formula, to this model. So it will be like external var plus epsilon. Yeah. Okay, so it's nice. Yeah, here we describe our variables. Yeah, we can write this formula for each components of vector y, and we add some hypotheses, add some restrictions to our model. So each of the nodes are independent between each other, or uncorrelated between each other. So I guess this is not. So yeah, I will add for myself some kind of tag that uncorrelated is not equal to the independent. So as I know, if some variables are independent, it means that they are uncorrelated. But it doesn't follow in the right way. So if the variables are uncorrelated, they could be not independent. Okay, and we have this this property that variance must be infinite. Almost this, all its random has the same infinite variance. Even variable is now one of functions under which yeah. Also required for the standard cost. So okay, well, I think we use it. We use it like we use it, yeah. Is described below that below, yeah, next topics, or maybe here somewhere. So we will get the best estimate with our approach, with one of the approach. But to prove it, we need to have this restriction. One of the way to calculate this ordinary. So okay, what we will do, we will define difference between actual value of our target and our model, and yeah, our error, yeah, and we will minimize our error, so we can here we can define our errors, and after that, yeah, we will try to minimize it. Okay, so let it be so. So we will got another approach for this, and after that we will find the minimum of it just with using derivatives. We found derivatives, and after that we what we do, we yeah, we find formula for our weights. Okay, so yeah, so another way to to formulate or to find a solution here is another approach. It's called maximum likelihood estimation. So so here the only thing that we consider it is that error is normal distribute. So here we actually consider that its mean 0, its standard deviation is also infinite, I guess, and yeah, well, I think we can prove that noises are also uncorrelated, but I'm not sure we can do it. But let us now assume I think there is some kind of things that could help us with topic. Okay, let's rewrite the model from a new perspective. Okay, so since the example are taken independently, uncorrelated errors is one of the. Okay, so we still have uncorrelation here. The full life of the data will look like production of density. Let's consider the log likelihood, which allows us to switch products. Okay, so we take log from our formula, from this one, and product will be converted into the and sum will be transferred into the product. Yes. Okay, so yes, so not so sure how to. So these examples are taken randomly. The full that will look like a product. So well, no, I think there must be some, and here must be product. Like okay, so Okay, let's do some break. I will try to learn some fast typing things. So maybe not this time. Go to the break, I guess. Okay, so let's continue. Okay, so I'm not sure why here we have product, because here we have y I. So we had formula that that declares that we should sum all of this. Yeah, this one we should sum all of it, and here we should have sum instead of product. And yeah, so we have what we have. Have log product of something. So if we will use one of the properties of logarithm, will be sum of the logarithms that are here. Okay. Yeah, I think they did mistake. Here must be product, yeah. Okay, and check it maybe. Article 1. So the main question here is why do we need here product instead of yeah, okay, so and another question, how do we get last question? So you should well, I need to check like break. Be right back. Плохо пахнет. Она не сильно работает или? То есть прям сейчас, например, сильно совсем работает? Машинка. Sorry. Well, so where I was. Okay, so I didn't understand what was this, why, like this one, this sum is equal to this one. So how do I get it? So we got this thing, and we want to find the maximum likelihood hypothesis. So we need to maximize expression to get WL, maximum likelihood. It's the same as maximizing the logarithm. Note that while maximizing the function over some parameters, you can throw away all numbers that do not depend parameters. So we don't need this first expression, so we can get rid of it. Okay. Okay, so and this one is equal to our summation here. How do we call it? The mean squared error, yeah. And in order to maximize this one, we need to find minimum of squared error. Because we have minus here. Turns it out that such a cost function is fact that there bias against decomposition. Let's talk a little about error properties. In fact, this discussion let's talk a little about the error properties of linear regression prediction. In fact, this discussion is valid for all machine learning algorithms. We discover the following. True value of target variable is the sum of deterministic function and random error. Yeah, it's true. Okay, so error is not distributed with zero mean and some variance. So why thus we have seen that the mixation turns out that such a fact that the error I'm not sure how does it follow. The value of target is the sum of deterministic error. Okay, so yeah, it was true. So we have some sample of data, so is the deterministic one is determined. Okay, so error are normally distributed. Okay, true value target variable is also normally distributed. Also fine. We try to approximate a but unknown function using a linear transfer. I don't know where was that. The error, the point decomposes follows. Okay, for clarity, annotation. Annotation argument each correctly. Those two are easily decomposed according to formula variance. And finally, we get to the last term in the sum. Finally, let's bring this all together. So maybe I should try to write it by myself. So okay, what we have in the beginning. So power 2. So okay, here we just use the properties of mean, of average, of mathematical mean. Okay, so and what we are doing here, variance of y is equal to mean, mathematical mean of y square minus mathematical mean and this one in square. Am I correct? Yes, I'm correct. So next. And yeah, well, what is I'm not sure what is. So I think the original yes, I think original definition this one is this one. So I think um, in square. So if we like imply this operation to this function, we can simplify it to this form. Okay, so what's next? What's next? Yeah, well, and we can use variance to describe it again, like expectation from y in square is equal to var variance square minus and square. Okay, so and similarly to the next. So the square is equal to to same. And how do they what they did with the yeah, with the third one? So Mm, so this thing is equal to f in square. This thing is equal to excitation of f in square. And variance of y is equal to the sigma in square. Well, we don't know actually about expectation of f in square. So so what we have from here. So this one is equal to sigma in square minus f in square. So is it correct? Change. Here must be plus. Yeah. I did wrong. So yeah, here must be plus. Okay, so here we have plus as well, and plus as well. F is, um, plus bar bar f station and minus mean of f. And what are they doing with? So bit of y as they write y is equal to epsilon. So So if epsilon and that, so f we got to the last. Recall that the error and the target variable are independent of each other. Um, okay, so uh, plus var. Yeah, well, I will finish this this month, so and after that I will go to the break. So okay, var where I'm var f plus v minus f minus f. Yes, so sigma f variance. Yeah, and the last one is equal to 0. Because expectation of error is equal. Okay, so okay, so and we will group f an expectation of an expectation of estimation of f in one group. So we will get squared bias, I guess. That's how it's called. Is the average error for all sets of data variance? Is error variability, or by how much error will vary if we train the model on different sets of data? Irremovable error. While we cannot do anything with sigma in square term, we can influence the first two. Ideally, we would like to negotiate both of these terms, upper left, but in practice, it often is to bounce between the biased and unstable estimate high variance. Yes, so generally, as mentioned, as the model becomes more computational, when the number of free parameters grows, the variance version of the estimate also increases, but bias decreases due to the fact that the training memory is complete. Small changes lead to unexpected results. On the other side, the model is eternal. offset. Plasma. Then the OLS. Estimated pointer of the line is the best for the class of linear. This means that if there exists any other unbiased model from the same class of linear modes, sure. Okay, so not not sure that I understand perfectly the last part, but I will go after with this, or maybe not. Okay, so one more time this thing. So we got our formula for error, and that's formula tell. Well, regularization of linear situation where height tension is the bias for sake of stability. Use the variance of one of the conditions of the Gauss-Markov theorem is calm rank. Otherwise, the solution doesn't exist since the inverse matrix doesn't. In other words, will be singular. This problem is called an ill-posed problems. Yeah, so yeah, I will do this Pomodoro. I will spend this Pomodoro with MLcourse, I guess. Often we deserve the so-called multi problem like this must be corrected. Namely, matrix needs to become non-generate or regular. By this process called regulation. Often we observe the so-called multi-correlated data. When two or more features are strongly correlated, it's manifested in the matrix X form of almost independent problem or prediction attributes area. What is going on? Balcony. Two or more features are strongly correlated, manifested in the matrix form of almost linear in the columns. For example, in the problem of predicting house prices by their parameters, attributes area with balcony and area without balcony will have an almost linear relationship. Formally, matrix such data is reversible, but due to motive sum of value will be 0. In the inverse matrix, some extremely large edge value will appear, so as edge values of the inverse matrix are inverses. The result of this vacillation of eigenvalues is a stable estimate of parameters. Adding a lead to computation. One method of regularization is Tikhonov, which generally looks at the addition of new member to the Minsk. Tikhonov matrix is often expressed as the product of a number by in this case the problem of the means error becomes problem with the on L2 if the new function with respect to the model tells the problem. This type of regression is called rich regression. The rich is a diagonal that we have to ensure that we get a regular matrix. Such solution reduces dispersion, becomes biased because the norm parameter makes the solution shift toward. On the figure below, the solution is section I dot line. Two dots represent different can be set by lambda. Okay. So let's try to start logistic regression. So the basic idea behind the linear classifier is that the two variable values of the target class can be separated by a hyperline in the feature space. If this can be done without error, the training set is called linearly separable. We have already seen linear regression and ordinary least squared squares. Let's consider a binary classification problem and denote target classes to be +1 positive example and -1 negative example. One of the simplest linear classifier can be defined using regression as follows. Okay, so we calculate the sum and we want to return sign of this sum. Okay. Logistic regression as a linear classifier. Logistic regression is a special case of linear classifier, but it has an added benefit of predicting a probability p plus of referring example xy to the class x to the class plus. So we also will get probability of this event. Being able to predict not just the response but the probability of assignment to class +1 is a very important requirement in many business problems. Credit scoring where this application is traditionally used. Customers who have applied for a loan are ranked based on this predicted probability to obtain a scoreboard that rates customers from bad to good. Below is an example of such a toy scoreboard. Okay, the bank chooses a threshold. Reduce the probability of loan default. This picture is 0.15 and stops approving loans starting from that value. Moreover, possible to multiply this predicted probability by the outstanding amount to get the expectation of losses from the client. And also good business metrics. This is the probability. We can start by constructing a linear prediction using OLS, but converting the result value to the probability range. This relation uses function for this. Now let's understand what are prerequisites. Okay, so one more time. To predict this, we can start by constructing a linear prediction OLS, but converting. Okay, so okay, so we build this prediction, and after that we convert it into number from 0 to 1. So where it will be 1, where it will be 0, I mean. Think nowhere, yes, and it will be 1 if z will be equal to 0. No. No. Also nowhere, I guess. Well, okay, so it seems. Okay, never mind. Function sigma. So we build sigmoid. Let's know the probability of an event x as px. Then the odds ratio or determined by which is the ratio of the probabilities of whether or not an event will happen. It's obvious that probability and odds ratio contain the same information. But while px from range from 0 to 1 or r is in range of 0 to we calculate the logarithm of OR algorithm odds or log probability ratio. It's easy to notice that log. Yes, so this is what we will use with OLS. Let's see how logistic regression will make prediction. Now let's assume that we have how obtained weights train the model. That we will look how. Okay. Step 1. Calculate the sum. Compute the log odds ratio. Now that we have the example to the class let class. The rest set you see that we have sigmoid function. So logistic regression predicts the probability of assignment. We will see how the model is trained. We will again rely on the maximum. Maximum logistic regression. Now let's see how an optimization problem for logistic regression is obtained from Y. Namely, minimization of the class function. We have just seen that logistic regression model, the probability of an example to the class. Then for class minus, corresponding expression is both of the expression can be cleverly combined into one. The expression is known as the margin of classification object, also called margin. Not negative, the model is correct in choosing class of the object. If it's negative, the object not the. That's exactly why we have to such conclusion. Let us turn to the geometrical interpretation of classifier. First, I recommend looking at classic reduction problem and find the distance from the point, the radius vector xi to plane defined by the equation. Answer when we get so it will be like some solution from that one and divided by okay. When we get to the answer, we will understand that the greater the absolute value of the expression, the farther the point xy is from the plane. Hence, our expression is kind of confidence of our model's classification of the. If the margin is large and positive, the class label is set correctly and the object is far away from the separating hyperplane. Classified confidently. See point x3 on x picture. If the margin is large and negative, and value is negative, yeah, that's also fine. If the margin is small, then the object is close to a separating hyperplane, and the margin sign determines whether the object is correctly classified. See point x2. Now compute the likely the data set. Probability of observing the given vector y from data set. As usual, let's take the logarithm because much easier to compute than the product. As likelihood is the minimization of the expression. This is logistic loss function over all objects. Okay. Yeah, well, lots of formulas, not so easy to understand. Picture reflects that if we are not able to directly minimize the number of errors, the problem we can minimize its upper bounds. Logistic loss function, while is simply the number of errors of logistic, those values auto-regularization of logistic is almost the same as in the case of ridge regression. Instead of minimizing the function, we minimize the following. In the case of logistic regression, reverse regression is typically introduced. Then the solution to the problem would be okay. Well, yeah, need like get through one more time. I think I will need to get through it one more time. Okay, maybe yeah, I will watch the video after everything. Yes, so let's go to the break. Okay, so I finished on the theory with logistic regression. Not sure, yeah, I didn't understand everything, but I think I got some idea. So, okay, well, let's continue with course. Where do I finish? Okay, so yeah, well, I think I finished the first part, but I did mistake. So let's start the. I remembered Venn diagrams. Ah, well, I finished. Yeah. Okay, so yeah, well, I finished the test. I guess this test for everything. This is a test for everything. So let's go. Campus following two-way data. This data for the of 100 students. What percentage of males had negative opinion on uh, do divide male's negative opinion by the I guess total. So 2% had negative opinion of so we have 36 negative opinion by male. Okay, maybe I need to divide it by total males. So I need to divide 36 by 36 plus 14, it will be 50 divided by, well, it will be 40%. The two-way frequency table below shows data on playing a musical instrument and playing sports for the students in George class. Georgia class. Okay, playing music instruments total. To the following statements about George class instruments. Students who do not play sports are more likely to play a music. Yes, so here we'll have 70% people who do not play sports but play music instruments, and we have 30%, okay, and who do play sports. So here we have 6 out of 40 is less, so the first statement is not true. Okay. The fewer students play both sport and the fewer students play both a sport and music. So it's also not true. Like this category is less, like, the fewest. The persons who do not play musical instruments and who do not play sports. Students who play musical instruments are more likely to play sports than students who play music are more likely to play sports. More students don't play sports than play more sport. More students. No, it's also not. Well, actually, that one is correct. Ah, yeah, yeah, got it. Yeah, I think the first one is then. Yeah, well, I mislead there, so yeah, I got it. The teams in the National Football League in America are divided into two conferences, AFC and FC. Some teams have animals as their mascots, and others do not. The following two-way table displays this data. Animal non. How many teams in the AFC have an animal mascot? 7. The relative frequency table below summarizes a survey about support for candidate X in upcoming national election. In this survey, 75 randomly selected opinions supported candidate X. Does the table show evidence of an between from California and pool? Oh, understand how it looks. So okay, so I think I got it. So sports candidate X. So okay, so 75 people in the first row or first line. It's 37% of everyone. So what I need to do is to divide this number by 0. So here we have 200 people, the first line. So means that 125 people from California supports candidate X. Okay. write it down. Okay, so Virginia, California, support, not support. Okay, so here we have 75, 105. Okay, so 75, it's also 30% of all Virginians. So 75 divided by 0.3. Okay, and here we have 200 and 100 and 50. So 175 is equal to 100 and 175 is the 70% of the all of those who oppose candidates. So 175 divided by 0.7 equal to no. So yeah, no. Again, so 175 divided by 0.5. Understand. So 1% by yes, it's 70, must be 73. So yes, yes. So we can actually check it. So one well, okay, so numbers are kind of strange. Try to okay, what does how many people in this survey were California? Okay, so I think okay, so if we have here we have 1 5, so there must we also must have this number. Okay, and Californians we had 2250. Okay, so does the table show evidence of an association between being from and X? So so Okay, we have 50 on 50. How many people do we have in so have to, I guess, yes, so oh, so easy time. Okay, let's try to make some conclusions. We have equal numbers of virgins and Californians. Yeah, Californians and yeah, they like divided equally on those who support candidate and those who not support, and from Virginia we have some kind of opposite station. Most of them are not supports. Let's try to come. Yes, because okay, so and this one, so 25% of people. So if we want to like to find connection, well, yeah, actually, yeah, well, I think these mm, this true wave frequency table below shows data on twins in patients' family history and pregnancies with twins pregnancies Dr. Ward has attended. Complete the following two-way table of raw data on twins pregnancy with twins. Ah, no, no. 8 by 26 plus 8, it is 34. Here we will have 4. Here we will have 70, 0.70. We'll have 5. This one plus this one will be we will have 0.8. James is interested in the relationship between weather conditions and whether the downtown train runs on time. For year, James records the weather each day as well. The weather, train, Okay, so we have the same problem close to this problem, so do it after the break. So okay. Here is some delay. Okay, find the marginal distribution of weather conditions. Well, marginal, I think, was okay. What is the sum of total? We have total. Oh, so the sum must be 100, but 51, 46. Um, conditional. So well, actually, I find the measure of weather condition. Weather condition. Well, I think found. Well, I think weather. So could be it's collected data about sources of pets. So graph of which belong kind of pet and uh well, so shelter must be, 40%. But what? So So yeah, I think it's conditions pet dogs, conditions emergency wish for pet sorts. James just James moved boxes from the living room after rooms had the same, so it is bedroom. The graph is the number of students with brown eye is the number of students with green and blue. So with brown eye is green and blue. Green 4, 8 less. So it must be greater than. So with brown eye is 14, must sum of them is 20, so 20. Theory. Next inventory search. So data set contains 3 variables. One of them are categorical. The table below shows and all the following information about box of 18 is of chocolate and contain 20 have is collect about have region, Democrat, and that is okay. So we have Republican, Midwest. So well, it's not correct because not even the half of them. So actually, yeah. So we have in Southeast region we have more Republicans, so they perceive higher in Midwest. So more likely that he is Republican, that he is from South. Even that it's certain that presents. Yeah, it's not. It's certain because we have only one of them. Okay, let's check the last one. Even this is then this likely the designator is Republican. Yeah, it's also true. I think the last one is more true because we don't know actually we don't have information about all of them. So I think last one is why not? Is sentiment. Yeah, it had it. Authors counts. Ah, we need two. Yeah, yeah. I I wasn't sure. Yeah, I thought it only one answer. Okay, so I think this this was first topic. Closing categorical data. So I think the next topic is quantitative data with.
What I want to do in this video is think about all of the different ways that we can represent data. So right over here, we have a list of, and I'm just using this as one form of data, a list of student scores on, say, the last test. So Amy got 90% right, Bill got 95% right, Cam got 100% right, Efra also got 100% right, and Farah got 80% right. This is one way to show data. Remember, data is just recorded information, and it could be numeric like this, it could be quantitative, so you're recording actual numbers, or it could even be things, you could record data on how did they like the test, and they could have scored it based on I really liked it, I kind of liked it, I didn't like it. Or they might have rated it on a scale of 0 to 5, which would have been numbers, but it's numbers that are measuring people's opinions, as opposed to here, we have numbers that are measuring their actual scores. So there's all different types of data, and I don't want to get into all of that, but let's just start thinking about different ways ways to represent this data. So this is one way. You could view this as a table where you have the name and then you have the score. So you have your name column and then you have your score column, and I could construct it as a table. So it clearly looks like a table like that. That's one way, one very common way of representing data, just like that. That's actually how most traditional databases record data, in tables like this. But you could also do it in other ways. So you could record it as a oftentimes called a bar graph or sometimes a histogram. So you could put score on the vertical axis here, and then you could have your names over here. And let's see the scores. Let's see, maybe I'll make this a 50. Actually, let me just mark them off. So this is 10, 20, 30. No, that's too big. 10, 20, 30, 40, 50, 60, 70, 80, 90. So that's, and then 100. So that's 100. 1, 2, 3, 4, 5. That would be 50 right over there. And then you could go person by person. So Amy got a 90 on the exam. So the bar will go up to 90. So that is Amy. And then you have Bill got a 95. So it's going to be between 90 and 100. So it's going to be right over there. Bill got a 95. And so it would look like this. Bill. So that is Bill. And then you have Cam, who got 100 on the exam. So make sure, obviously I'm hand drawing it, so it's not as precise.
Okay, we have this representation like before. I think it's nothing new. There is nothing new here.
Precise as if I were to do it on a computer. So this right over there, that is Cam's score. Ephra got the same score as Cam. So her score is going to be, let me do that in the color, in Ephra's color. And that's Ephra's score right now there. She also got 100. So Ephra. And then finally Farah got an 80. So 60, 70, 80. So Farah got an 80. So this is Farah's score right over here. So this is another way of representing the data. And here we see it in visual form, but it has the same information. You can look up someone's name and then figure out their score. Amy scored a 90. Bill scored a 95. Cam scored 100. Ephra also scored 100. Farah scored an 80. And there's even other ways you can have some of this information. In fact, sometimes you might not even know their names, and so then it would be less information, but it might just be a list of scores. The professor might say, hey, here are the 5 scores that people got on the exam, and they would list 90, 95, 95, 100, 100, 100, and 80. Now, if it was listed if this was all of the data you got, this would be less information than the data that's in this bar graph or this histogram, or the data that's given in this table right over here. Because here, not only do we know the scores, but we know who got what score. Here, we only know the list of scores. But there's even other ways, and this is not an exhaustive video of all of the different ways you can represent data. You could also represent data by looking at the frequency of scores. So the frequency of scores right over here. So instead of writing the people, you could write the scores. So let's see, you could say this is 80, 85, 90, 95, and 100. And then you could record the frequency that people got these scores. So how many times do you have a score of an 80? Well, Farah was the only person with a score of 80, so you put one data point there. No one got an 85. One person got a 90, so you put a data point there. One person got a 95, so you could put that data point right over there. And then 2 people got 100. So this is 1 and 2. Let's see, the other 100 is in this color, so I'll just do it in the color. You wouldn't necessarily have to color code it like this. So this is another way to represent. And this is, this axis, you could just view this as the number. So this tells you how many 80s there were, how many 90s there are, how many 95s, and how many 100s. So this right over here has the same data as this list of numbers. It's just another way of looking at it. And once you have your data arranged in any of these ways, we can start to ask interesting questions. We can ask ourselves things like, well, what is the range of data? What is the range in the data? And the range is just the spread between the lowest point and the highest point. So the range in this data is going to be the difference between the highest score, and the highest scores are 100, and the lowest score, and 80. So the range is going to be the difference between the max minus the min, the maximum score minus the minimum score. So it's going to be 100 minus 80 is equal to 20. So that gives you a sense of things. It kind of gives you a sense of spread. You could also ask yourself, well, how many people scored below 100? And these are just interesting questions. Below 100. And you can actually answer that question. Well, actually, you could have answered either of these questions with any of these different ways of looking at the data. If you say how many people scored below 100, well, 1, 2, 3. How many people scored below 100? Well, 100 is up here, so it's going to be 1, 2, 3. How many people scored below 100? 1, 2, 3. How many people scored below 100? 1, 2, 3. And so any way you look at it, you would have gotten 3. And you could also ask yourself, what is the most frequent score? So most frequent. Most frequent. And once again, you can answer that question with any of these ways of representing this data. You can look at our original table and you say, look, there's only 190, 195, 180, there's 200s. So you'd say, look, there's the most frequent score is 100. You'd see that over here too. You actually have 200s. There's only one of each of the other scores. Here you also see the 200s. And here is probably the clearest if you're looking at frequency. Sometimes this might be called a frequency plot. Sometimes it's called sometimes the official, it's often called a frequency plot. And you see here, the most frequent one is the one that has the most dots on it, which is 100. So anyway, that's just a very high level overview of how you can look at data and different ways to represent data. But the one thing I really want you to get from this is that these are all different ways of representing the same data. And we could probably invent other ways of doing it as well.
Okay.
What I have here is the list of ages of the students in a class. And what I want to explore in this video is different ways of representing this data and then see if we can answer questions about the data. So the first way we can think about it is as a frequency table. Frequency table. Frequency table. And what we're going to do is we're going to look at for each possible age that we've measured here, see how many students in the class are of that age. So we could say the age is one column, and then the number of students of that age, or we could even say the frequency Frequency. When people say, how frequent do you do something? They're saying, how often does it happen? How often do you do that thing? Frequency. Or we could also say, actually, let me just write number. I'm always a fan of the simpler. Number at age, which we could also consider the frequency at that age. The frequency of students. All right. So what's the lowest age that we have here? Well, the lowest age is 5. So I'll start with 5. And how many students in the class are age 5? How frequent is the number 5? Let's see. There's 1, 2. Let me keep scanning. Looks like there's only 2 5s. So I could write a 2 here. There are 2 5s. And now let's go to 6. How many 6s are there? Let's see. There's 1 6. There's only 1 6-year-old in the class. All right. 7-year-olds. Let's see. There's 1, 2, 3, 4 7-year-olds. 4 7-year-olds. Now, what about 8-year-olds? 8-year-olds, I'm going to do some color that I have not used yet. 8-year-olds, we have no 8-year-olds. 0 8-year-olds. And then we have 9-year-olds. Let's see. 9-year-olds, we have 1, 2, 3, 4 9-year-olds. 4 9-year-olds. 10-year-olds, what do we have? We have 1 10-year-old right over there. And then 11-year-olds. 11-year-olds, there are no 11-year-olds. And then, let me scroll up a little bit. And then finally, 12-year-olds. 12-year-olds, there are 1, 2 12-year-olds. So what we have just constructed is a frequency table. It's a frequency table. You can see for each age how many students are at that age. So it's giving you the same information as we have up here. You could take this table and construct what we have up here. You would just write down 2 5s, 1 6, 4 7s, no 8s, 4 9s, 1 10, no 11s, and 2 12s. And then you would just have this list of numbers. Now, a way to visually look at a frequency table is a dot plot. So let me draw a dot plot right over here. So a dot plot. And a dot plot, we essentially just take the same information and even think about it the same way, but we just show it visually. So in a dot plot, what we would have, actually, let me just not draw an even arrow there. We have the different age groups. So 5, 6, 7, 8, 9, 10, 11, and 12. And we have a dot to represent, or we use a dot for each student at that age. So there's 2 5-year-olds, so I'll do 2 dots. 1 and 2. There's 1 6-year-old, so that's going to be 1 dot right over here. There's 4 7-year-olds, so 1, 2, 3, 4. You have to count all of them to kind of come up with this. And so subtract from 5. You find the difference between 12 and 5, which is 7. Here, you do not have to do it. You still could have done it. You say, okay, what's the lowest? Let's look at 5. Are there any 4s here? Nope, there's no 4s. So 5 is the minimum age. And what's the largest? Is it 7? No. Is it 9? 9, no, 10? No, 12. 12. Are there any 13s? No, 12 is the maximum. So you say 12 minus 5 is 7 to get the range. But then we could ask ourselves other questions. We could say, how many older than 9 is a question we could ask ourselves. And then if we were to look at the dot plot, we say, okay, this is 9, and we care about how many are older than 9. So that would be this 1, 2, and 3. Or you could look over here, how many are older than 9? Well, it's the 1 person who's 10, and then the 2 who are 12. So there are 3. And over here, if you said how many are older than 9, well, then you would just have to go through the list and say, okay, no. Okay, here, 1, 2, 3, and then not that person right over there. So hopefully this is just an appreciation for yet another 2 ways of looking at data.
Okay. Dot plots and frequency tables. Frequency tables. I think it's quite open.
So let's say you were to go to a restaurant, and just out of curiosity, you want to see what the makeup of the ages at the restaurant are. So you go around the restaurant and you write down everyone's age. And so these are the ages of everyone in the restaurant at that moment. And so you're interested in somehow presenting this, somehow visualizing the distribution of the ages. Because you wanted to say, well, are there more young people? Are there more teenagers? Are there more middle-aged people? Are there more seniors here? And so when you just look at these numbers, it really doesn't give you a good sense of it. It's just a bunch of numbers. And so how could you do that? Well, one way to think about it is to put these ages into different buckets, and then to think about how many people are there in each of those buckets. Or sometimes someone might say, how many in each of those bins? So let's do that. So let's do buckets or categories. So sometimes it's called a bin. So the bucket, I like to think of it more as a bucket. The bucket, and then the number in the bucket. The number in the bucket. I'll just write the number. It's the number. It's the number in the bucket. All right. So let's just make buckets. Let's make them 10-year ranges. So let's say the first one is ages 0 to 9. So how many people, and let me define all of the buckets here. So the next one is ages 10 to 19, then 20 to 29, then 30 to 39, and 40 to 49, 50 to 59. Make sure you can read that properly. Then you have 60 to 69. I think that covers everyone. I don't see anyone 70 years old or older here. So then how many people fall into the 0 to 9-year-old bucket? Well, it's going to be 1, 2, 3, 4, 5, 6 people fall into that bucket. How many people fall into the 10 to 19-year-old bucket? Well, let's see. 1, 2, 3. 3 people. I think you see where this is going. What about 20 to 29? So it's 1, 2, 3, 4, 5 people. 5 people fall into that bucket. All right. What about 30 to 39? We have 1, and that's it. Only 1 person in that 30 to 39 bin or bucket or category. All right. What about 40 to 49? We have 1, 2 people. 2 people are in that bucket. And then 50 to 59. So you have 1, 2 people. 2 people. And then finally, ages 60 to 69, use a different color, 60 to 69, there is 1 person right over there. So this is one way of thinking about how the ages are distributed, but let's actually make a visualization of this. And the visualization that we're going to create, this is called a histogram. Histogram. We're taking data that can take on a whole bunch of different values. We're putting them into categories, and we're going to plot how many folks are in each category. How big are each of those categories? And actually, I wrote histogram. I wrote histograph. I should have written histogram. So a histogram. So let's do this. All right. So on this axis, let's see. The largest category has 6. So this is the number of folks, and it's going to go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is the number. And on this axis, I'm going to make buckets. The buckets. And let me scroll up a little bit now that I have my data here. I'm going to have to look at my data set again. So I have 1 bucket. This is going to be the 0 to 9 bucket right over here. 0 to 9. Then I'm going to have the 3. Actually, let me just plot them since I have my pen that color. So in 0 to 9, there are 6 people. 0 to 9, there are 6 people. So I'll just plot it like that. And then we have the 10 to 19. There are 3 people. So 10 to 19, there are 3 people. So I'll do a bar like this. Then 20 to 29, I have 5 people. 69, we have 1 person. And what I have just constructed, I took our data, I put it into buckets that are kind of representative of the categories I care about. 0 to 9 is kind of young kids.
Okay, so yeah, I will finish this video after break, well, but in general it's quite fun. So yeah, well, I think last Pomodoro, yeah, I will spend also on course. I kinda keep some of this, and I don't really want to go through the theory again today, so yeah, I will finish one Pomodoro, and after that, yeah, revise goal. Maybe not for full Pomodoro, but some part of it. So let's finish. Say for this histograms.
To 19, I guess we call them adolescents or roughly teenagers, although obviously if you're 10, you're not quite a teenager yet, and then all the different age groups. And then when I counted the number in each bucket and I plotted it, now I can visually get a sense of how the age is distributed in this restaurant. This must be some type of a restaurant that gives away toys or something, because there's a lot of younger people. Maybe it's very family friendly. So every adult that comes in, maybe there's a lot of young adults with kids and or maybe grandparents up here, and they just bring a lot of kids to this restaurant. So it gives you a view of what's going on here. Just a lot of kids here, a lot fewer senior citizens. So once again, this is just a way of visualizing things. We took a lot of data that can take multiple data points. Instead of plotting each data point like we might do in a dot plot, instead of saying how many 1-year-olds are there, well, there's only one 1-year-old. How many 3-year-olds are there's only one 3-year-old. That wouldn't give us much information. We just have like these single dots if we were doing a dot plot. But as a histogram, we're able to put them into buckets. And we're like, hey, generally between ages 0 and 9, we have 6 people. And so you see that plotted out just like that. And obviously this doesn't apply just to ages of people in a restaurant. It applies to all sorts of data that you might want to collect and observe.
Okay.
Let's say that you have a cherry pie store, and you've noticed that there is variability in the number of cherries
I
on
think
each pie that you
this
sell.
is
Some pies might have over 100 cherries.
opposite task. So before we had like some sort of raw data, and we visualize it with histogram. Here we have opposite situation. We have histogram, and I think we will somehow like create some data.
While other pies might have fewer than 50 cherries. So what you're curious about is what is the distribution? How many of the different types of pies do you have? How many pies do you have that have a lot of cherries? How many pies do you have that have very few cherries? How many pies are in between? And so to do that, you set up a histogram. What you do is you take each pie in your store. Let's see if I can draw a pie of some kind. It's a cherry pie. I don't know if this is an adequate drawing of a pie. But you take each of the pies in your store and you count the number of cherries on it. So this pie right over here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say you keep counting, and let's say it has 32 cherries. You do that for every pie. And then you created buckets because you don't want to create just a graph of how many have exactly 32. You just want to get a general sense of things. So you create buckets of 30. You say how many pies have between 0 and 29 cherries? How many pies have between 30 and 59, including 30 and 59? How many pies have at least 60 and at most 89 cherries? How many pies have at least 90 and at most 119? And then how many pies have at least 120 and at most 149? And you know that you don't have any pies that have more than 149 cherries, so this should account for everything. And then you count them. So for example, you say, okay, 5 pies have 30 to 59 cherries. And so we create a histogram, or you create a histogram, and you make this magenta bar go up to 5. So that's how you would construct this histogram. That's what this pies at different cherry levels histogram is telling us. So now that we know how to construct it, let's see if we can interpret it based on the information given in the histogram. So the first question is, based on just this information, can you figure out the total number of pies in your store, assuming that they're all accounted for by this histogram? And I encourage you to pause the video and try to figure it out on your own. Well, what's the total number of pies? Well, let's see. There's 5 pies. There's 5 pies that have more than 30 or more, have at least 30 cherries, but no more than 59. You have 8 pies in this blue bucket. You have 4 pies in this green bucket, and then you have what is this? 5? No, this is 3 pies that have at least 120, but no more than 149 cherries. And this accounts for all of the pies. So the total number of pies you have at the store are 5 plus 8 plus 4 plus 3, which is what? 5 plus 8 is 13, plus 4 is 17, plus 3 is 20. So there are 20 pies in the store. Then you can ask a more nuanced question. What if you want to know the number of pies with more than 60 cherries? The number of pies with more than 60. So number of pies with, let's say 60 or more, 60 or more, 60 or more cherries. So let's think about it. Well, this magenta bar doesn't apply because these all have less than 60. But all these other bars are counting pies that have 60 or more cherries. This is 60 to 89. This is 90 to 119. This is 120 to 149. So it's going to be these 8 cherries that are, these 8 pies that are in this bucket, plus these 4 pies, plus these 3 pies. So it is going to be essentially everything but this first bucket. Everything but all the pies except for these 5 pies have 60 or more cherries. So it should be 5 less than 20. And so it's 8 plus 4 is 12 plus 3 is 15, which is 5 less than 20. So using this histogram, we can answer a really interesting question. We say, oh wait, how many more pies do we have that have 60 to 89 cherries than 120 to 149 cherries? Well, we say, well, we have 8 pies that have 60 to 89 cherries, 3 that have 120 to 149. So we have 5 more pies in the 60 to 89 category than we do in the 120 to 149 category. So a lot of questions that we can start to answer. And hopefully this gives you a sense of how you can interpret histograms.
Yeah, I think it's like we can calculate everything we need from this histogram. Not everything, but lots. This by grouping data. Pin is plotted as a bar. Pins are buckets. Reading history of the bars tell us how many are in each. Example, pumpkin, 6 and 9. Okay. Okay. You want to learn creating histogram? driving this. No strict how many. We're using to
A statistician for a basketball team tracked the number of points that each of the 12 players on the team had in one game, and then made a stem and a leaf plot to show the data. And sometimes it's called a stem plot. How many points did the team score? And when you first look at this plot right over here, it seems a little hard to understand. Understand you have 0, 1, 2. Under leaf, you have all of these digits here. How does this relate to the number of points each student or each player actually scored? And the way to interpret a stem and leaf plot is the leaves contain, at least the way that this statistician used it, the leaf contains the smallest digit, or the ones digit, in the number of points that each player scored, and the stem contains the tens digits. And usually the leaf will contain the rightmost digit, or the ones digit, and the stem will contain all of the other digits. And what's useful about this is it gives kind of a distribution.
then made a stem and leaf plot. So okay.
Of where the players were. You see that most of the players scored points that started with a 0, then a few more scored points that started with a 1, and then only one scored points that started with a 2, and it's actually 20 points. So let me actually write down all of this data in a way that maybe you're a little bit more used to understanding it. So I'm going to write the zeros in purple. So there's, let's see, 1, 2, 3, 4, 5, 6, 7 players had 0 as the first digit. So 1, 2, 3, 4, 5, 6, 7. I wrote 7 zeros. And then this player also had a 0 in his ones digit. This player, I'm going to try to do all the colors. This player also had a 0 in his ones digit. This player right here had a 2 in his ones digit, so he scored a total of 2 points. This player, let me do orange. This player had 4 for his ones digit. This player had 7 for his ones digit. Then this player had 7 for his ones digit. And then, let me see, I'm almost using all the colors. This player had 9 for his ones digit. So the way to read this is you had one player with 0 points, 0, 2, 4, 7, 9, and 9. But you can see, I mean, it's kind of silly saying the 0 was the tens digit. You could have even put a blank there, but the 0 lets us know that they didn't score anything in the tens place. But these are the actual scores for those 7 players. Now let's go to the next row in the stem and leaf plot. So over here, all of the digits start with, or all of the points start with 1 for each of the players, and there's 4 of them. So 1, 1, 1, and 1. And then we have this player over here. It's his ones digit, or her ones digit is a 1. So this player, this represents 11. 1 in the tens place, 1 in the ones place. This player over here also got 11. 1 in the tens place, 1 in the ones place. This player, let me do orange. This player has 3 in the ones place. So he or she scored 13 points. 1 in the tens place, 3 in the ones place, 13 points. And then I will do this in purple. This player has 8 in their ones place. So he or she scored 18 points. 1 in the tens place, 8 in the ones place, 18 points. And then finally, you have this player that has 2, the tens digit is a 2, and then the ones digit is a 0. I'll circle that in yellow. It is a 0. So he or she scored 20 points. So looking at the stem and leaf plot, we were able to extract out all of the number of points that all of the players scored. And once again, what was useful about this is you see how many players scored between 0 and 9 points, including 9 points, how many scored between 10 and 19 points, and then how many scored 20 points or over. And you see the distribution right over here. But let's actually answer the question that they're asking us to answer. How many points did the team score? So here we just have to add up all of these numbers right over here. So we're going to add up, I'll start with the largest. So 20 plus 18 plus 13 plus 11 plus 1 is 12, 36, 40, 12, 13, 22, 28, 9, 10. So we get to 102 points. The team in total.
So in the stem we have like the first number. In the leaf we have
the government created the following stem and leaf plot showing the number of turtles at each major zoo in the country. How many zoos have fewer than 46 turtles? So what the stem and leaf plot does is it gives us the first digit in each number, and essentially you could call this the tens place, and then it gives us the ones place. So there's only one zoo that had 4 turtles, so you could do this as 0, 0, 4, or 4 turtles. Then there's, well, let's see, so everything here, the tens place is a 1, so this number right over here is really an 11. This is a 14. This right over here would be a 16, that's a 16, and so forth and so on. This would be a 17, 18. All of this is 23, this is 23, this is 26, because we have our tens place right over here. This is the first digit. So let's go ahead and answer the question. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 zoos have fewer than 46 turtles. Let's do another one. The buyer for a chain of supermarkets created the following stem and leaf plot showing the number of coconuts at each of the stores. What was the smallest number of coconuts at any one grocery store? So the buyer for a chain of supermarkets created the following stem and leaf plot showing the number of coconuts at each of the stores. A statistician for a chain of department stores created the so this right over here represents 12 coconuts at that store. So we'll put 12 right over here. Let's try out another one. A statistician for a chain of department stores created the following stem and leaf plot showing the number of watches at each of the stores. How many department stores have exactly 7 watches? Well, that's only this one right over here. 0, 7 watches. This one right, this, and that one are not 7. This is representing 17 because it's in the stem and leaf plot showing the number. So that meets the criteria. And then
Okay. Well, the idea is quite fun. Zookeeper for how many zoos have exactly 20 bears? So 2. I will take a quiz, I guess, and I will spend I think the rest of the time on this going to it. I is a wildlife photographer. The following data points represent the number of his have been published in each local newspaper. Using the data, create a dot plot where each dot represents a local newspaper. So one of them has 1, 4, 5, and 2, 6. Following dot plot shows the height of each toddler as Miss Rare daycare. Each dot represents a different toddler. Okay, how many toddlers are in Rare's daycare? Okay, so 1, 2, 3, 5, 6, 7, 10. Data points represent the gap which can be say last. Points represent how many houses the visited. So each day. Okay, I got it. So from 0 to 10 we have one house. From 10 to 20 we have 1 to 2 houses. From 20 to 30 we have 1 house. So more than 30 we have house as well. The regional manager of chain department stores created the following step and leaf plot showing the number of pairs boots and each of the stores. Um, how many department stores have more than 6 Shows the number of pairs. So I think 0. Size of each bin, size of each house, area, number of houses. How many houses are on 4, 7, 4. Size of each number of houses times 8 plus plus okay 11. No, it's fine. It's 11 plus 9, 20 plus 20, 24. Okay, 25. Following data points represent the number of players on the Russian B volleyball team were injured in each match. Is that create a frequency table? So 0 number of matches. Okay, so I think 0. Every match we have injured. 1 we have 1, 2, 3 match, and also so what's
So what I want to talk about now are shapes of distributions and different words we might use to describe those shapes. So right over here, let's see, we're talking about Matt's Cafe, and we have different age buckets. So this is a histogram here. And in each bucket, it tells us the number of guests that are in that age bucket. So we don't have any guests that are under the age of 20. We have a reasonable number between 20 and 30. We have a lot of guests at 30 in that bucket between 30 and 40, reasonable number between 40 and 50. And then as we get older, we have fewer and fewer guests. So just when you look at something like this, a distribution like this, something might pop out at you. It kind of looks like, if you were to imagine this were an armadillo, this would be the body of the armadillo. And then what we see to the right would kind of look like the tail of the armadillo. And we actually use those types of words to describe distributions. So this distribution right over here, it looks like it has a tail to the right. It doesn't have a tail to the left. In fact, we have no one under the age of 20. But here, when we have a few people between 60 and 70, even fewer between 70 and 80, even fewer between 80 and 90, and if it kind of keeps going like this is a tail, and it's on the right side. It's a right-tailed distribution. So I'd call this distribution right-tailed. And I'm using Khan Academy exercises because it's a good way to see a lot of examples. And frankly, you should too, because it'll help you test your knowledge. But it's not left-tailed. Left-tailed, we would see a tail going like that. And frankly, if you're left-tailed and right-tailed, you're likely to be approximately symmetrical. Remember, symmetry, you define a line of symmetry, and one type of symmetry is one where if you were both sides of that line of symmetry are kind of mirror images of each other. You could fold over the line of symmetry and they'll roughly meet. And this one does not meet that, because if you were to say, hey, maybe there's a line of symmetry here, and you're trying to fold this over, it wouldn't match up. The two sides would not match up. So I feel good saying that it is right-tailed. So let's see, retirement of age of each guest. Well, yeah, these names aren't that great, but let's actually see what they're saying. They're saying by age, they're telling us the number of
left tail?
The line would be right at age 65. And this is a bucket for ages 60 to 70 to the right. These actually have fairly technical definitions when you get further in. Is to the left of your median and mode. That might not make any sense to you. You might just want to go after the tail. If you're left-tailed, you're probably left-skewed. If you're right-tailed, you're probably right-skewed. So let's keep going. Let's see if we can see. Let's actually see another example. So this is interesting. This is not, we're not given a histogram here. We're not given a bar graph. We're given a box and whiskers plot, which is really just telling us the different quartiles. So just to remind ourselves.
Yeah, well, this thing was in I think it was in the first lecture or in the second one with visualization. So I'm not so sure how I get it. So
this tells us the minimum of our data set, the bottom of our range. So the minimum value in our data set, we have at least 111. And then the maximum value of our data set, we have at least 125. Now this line right over here is the median. The middle number is 21. And then the box defines the middle 50% of our numbers. So it's kind of the meat of our distribution. So if we were to try to visualize what this would look like as maybe a histogram, and we don't know for sure because we might have a whole bunch of 11s, not so much that it skews this, but we could have more than one. But a distribution that this could match up with is something that looks like having a tail down here, and then you kind of bump up here. This is the meat of the distribution. It kind of looks something like that. And I can't draw because I'm doing this on the exercises right now. But for something like that, well, something like that would have a tail to the left. It has its range goes, fairly low to the left, but it might not have a lot of values there. If it had more values on the left side, this box would have been shifted over because a larger percentage would have been on the left, so to speak. And so this one, I feel pretty good about saying this is skewed to the left. It's definitely not symmetrical. If it was symmetrical, the median would be pretty close to the center. The box would be pretty centered. And it's not skewed to the right. If it was skewed to the right, you would have a tail to the right. You would have this whisker would likely be much, much, much longer.
Okay, so
in this video, I want to do some examples.
It was, yeah, this beans was in the lecture, I guess. So include that we met it here again. Well,
looking at distributions, in particular different features in distributions like clusters, gaps, and peaks. So over here, I want to do it with some examples. Which of the following are accurate descriptions of the distribution below? Select all that apply. So the first statement is the distribution has an outlier. So an outlier is a data point that's way off of where the other data points are. It's way larger or way smaller than where all of the other data points seem to be clustered. And if we look over here, we have a lot of data points between 0 and 6. And just think about what they're measuring. This is shelf time for each apple at Gorge's Grocer. So, for example, we see there's 1, 2, 3, 4, 5, 6, 7 apples that have a shelf life of 0 days. So they're about to go bad. You see you have 1, 2, 3, 4, 5, 6, 7, 8 apples that are going to be good for another day. You have 2 apples that are going to be good for another 6 days. And you have 1 apple that's going to be good for 10 days. And this is unusual. This is an outlier here. It has a way larger shelf life than all of the other data. So I would say this definitely does have an outlier. We just have this one data point sitting all the way to the right, way larger, way more shelf life than everything else. So it definitely has an outlier, and this one would be the outlier. The distribution has a cluster from 4 to 6 days. And we indeed do see a cluster from 4 to 6 days. A cluster, you can imagine, it's a grouping of data that's sitting there, or you have a grouping of apples that have a shelf life between 4 and 6 days, and you definitely do see that cluster there. And since I already selected 2 things, I'm definitely not going to select none of the above. So let me check my answer. Let me do a few more of these. Which of the following are accurate descriptions of the distribution below? And once again, we're going to select all that apply. So the distribution has an outlier. So let's see, this distribution, I do have a data point here that's at the high end, and I have another data point here that's at the low end, but I don't have any data points that are sitting far above or far below the bulk of the data. If I had a data point that was out here, then yeah, I would say that was an outlier to the right or a positive outlier. If I had a data point way to the left off the screen over here, maybe that would be an outlier, but I don't really see any obvious outliers. All the data, it's pretty clustered together. So I would not say that the distribution has an outlier. The distribution has a peak at 22 degrees. Yeah, it does indeed look like we have, and let's just look at what we're actually measuring, high temperature each day in Edgeton, Iowa in July. So it does indeed look like we have the most number of days that had a high temperature at 22, most number of days in July had a high temperature at 22 degrees Celsius. So that is a peak. You can see it. If you imagine this is kind of a mountain, this is a peak right here. This is a high point. You have at least locally, you have the most number of days at 22 degrees Celsius. So I would say it definitely has a peak there. Since I selected something, I'm not going to select none of the above. Let's do a couple more of these. Which of the following are accurate descriptions of the distribution below? So the first one, the distribution has an outlier. So let's see, this number of guests by day at Seth's sandwich shop. So let's see, the lowest they have no days where he had between 0 and 19 guests. No days where he had between 20 and 39 guests. Looks like there's about 9 days where he had between 40 and 59 guests. Looks like 20 days where he had between 60 and 79 guests. All the way, that looks like this is maybe 8 days that he had between 180 and 199 guests. But the question of outliers, there doesn't seem to be any day where he had an unusual number of guests. There's not a day that's way out here where he had like 500 guests. So I would say this distribution does not have an outlier. The distribution has a cluster from 0 to 39 guests. So 0 to 39 guests is right over here, 0 to 39 guests. And there's no days where he had between 0 and 39 guests, either 0 to 19 or 20 to 39. So there's definitely not a cluster there. I would say that the cluster would be.
So well, I think I will like finish this video.
were days that had between 40 and
Mm.
199 guests. Definitely not 0 and 39. There was no days that were between
I will
0.
do some short break, and after that I'll like try to finish just tutorial. I don't think that I will spend all this time for only this goal, so I don't think that it will be very long. So.
And 39 guests. So I would say none of the above very confidently. Let's do one more of these. Which of the following are accurate descriptions of the distribution below? All right. The distribution has a peak from 12 to 13 points. Let me see what this is measuring, or what this data is about. Test scores by student in Miss Frine's class. So you had one student who got between a 0 and a 1 on a 20-point scale. So got between, I guess you maybe out of 20 questions, got between 0 and 1 points. And then you see that no students got between 2 and 3, or 4 and 5, or 6 and 7. Then we have another student who got between 8 and 9. Looks like 3 students got between 10 and 11. And then we keep increasing. This looks like it's about 12 students got either 16 or 17, or something in between, maybe if you could get decimal points on that test. And then looks like 10 students got from 18 to 19. All right, so this says the distribution has a peak from 12 to 13 points. 12 to 13 points, there were 5 students, but this isn't a peak. If you just go to 14 to 15 points, you have more students. So this is definitely not a peak. If you were looking at this as a mountain of some kind, you definitely wouldn't describe this point as a peak. You would say this distribution has a peak. It has the most number of students who got between 16 and 17 points. So that's the peak right there, not 12 to 13 points. I would not select that first choice. The distribution has an outlier. Well, yeah, look at this. You have this outlier. Most of the students scored between 8 and 19 points. And then you have this one student who got between 0 and 1. It's really an outlier. You even see this, it's like unusually low or unusually high. So I would say this distribution definitely does have an outlier. And I'm not going to pick none of the above.
Yes, there wasn't like actually gaps. So well, I'll finish one. I will do the break, and after that I will finish this day of work today. Be right back. Okay, so yeah, let's go to my goals. Yes. So pass ML course in 1.5 months. So I think that's fine. So one. So today is uh, today is okay. So how much time does it? So it was 19 days or more than okay, so a little bit less than 3 weeks. So in this time, what I covered results covered 3 weeks. Uh, little oh. Okay, so set up the next certain time. So I think 1 month, 1 month will be fine. So 1 month will be 7. So it will be on 4th June. So okay, for yeah. So okay. So 2 or 3 competitions, 2 weeks. So maybe it would be as I didn't know in the beginning when I set up my goals, but actually this course includes this course includes some competitions from the Kaggle that are not like just like from them. So no, this is not competitions, study competitions. They're like uh, they're general competitions in the Kaggle. So I think yeah, I can like somehow like I can conduct these to concatenate them, join them. So it has like one list Kaggle on week 5 have, have six six yeah on week 6 we have Kaggle competition Alice competition. Uh, okay, so and do you have another one? Okay, so it actually has two competition one, so I think I can join these two goals. So how can I? well, I'm not. Okay, so yeah. Well, so I had like what, 1.5 months in this, so let's be 2 months. So yeah, I will have more time for course, and I will have more time for this task. So yeah, I think it's fine. So yeah, and I want to achieve at least one to get at least one achievement, like any achievement, like bronze medal or something. The one could be. So yeah, and after this, a month, yeah, I will get like what, something like, try to find something like connected with this area. So what's next? Okay, so what can I add? So yeah, well, I think so. If we consider that every week are the same, this time wise, correct. So we have, I covered 30% of the this course. 30% from 2 months is actually how much? Actually, it's actually, so 2 months is 6 days is, so 60 days is 2 months. So 10 days is no, 6 days is 10%. So well, actually I'm like doing fine in time wise. So actually I am on what I need to be approximately. So yeah, well, and I skipped a few days on last week, but it was like had some problems. So and I'll try to like keep my schedule week. I think it will be fine. Okay, so what's next? Well, I think I want to add some another goals. So yeah, it will help me with the last one. So my main goal, I so everything is made, but how can I so make? Well, what I want to add is I want to add some kind of like problems that I want to solve. Like, I mean, like problems, not only task or examples that I want to solve. So, for example, yeah, so I want to, so let it be what. So okay, so what I want to maybe okay pass maybe some probability course will be fine as well. So well, I want to be more specific. Maybe I will. So it will be 4th August. Time will be end. So okay. Well, let it be. I think. Well, let it be also. Like, so yeah, I want to like to get rid of some theory to this data for this date. So I think I can spread it. I'll build it. Space. So it's good to have this date for everything. Okay, so any competition. Let it be like after this dates the number of 4th September. Yeah, and here might be, so let it be October. So okay, so yeah, and what else I want to add will be like some kind of tasks, some kind of problems I want to like to solve, like some theoretical things, some tasks from here. So from statistics and probability course. So okay, for example, I want to solve like 2 tasks per day. So it will be 2 months. So it will be like so solve 100, 200. Same. Okay, so we have some dates. So yeah, I think I revise what I let it be. So yeah, well, maybe I will like, I don't know, I will add something here, or maybe I will remove something next time. So maybe yeah, maybe I will finish something as well. So in the next revision. So yeah, but anyway, I will try to keep this goals in mind. I will print something, so I will, so in order to have like visualization of goals, should be fine. So that's yeah. Well, I think yeah. The only thing that I don't like is like visualization of this. So accurate, I guess, clean and fancy. So maybe this like column is weird a little bit, empty, and in my opinion, right now I want to fill it only an expiration date in time, but exactly what I want. Okay, so yeah, well, maybe this plan is also not so good because it's actually like, I don't know, not so connected with the last one. Cause well, I will like solve these problems. I will pass these courses. I will like pass this course. I will get achievement. How does this help me to get the job? So, well, maybe I will need like to check job requirements before, like, in the meantime, in this time, while I'm passing this course. Cause well, I will like spend 3 months, and after that I will recognize that I don't get what I needed, so I will need to spend more time and so on. So not the best thing to do. So yeah, well, so the thing is, I do think that I all really need really need this goal, and maybe that's all. Three other is optional, so they just could help, but maybe not. Maybe think about it later. Easier for me. Thanks for watching. I will be I will usual things. I go for this course, and maybe yeah, for this course is not so great as I thought, but actually it has some good points somewhere. So see what some of these like topics are very easy, but some of them are actually, maybe I underestimate this course because sometimes it has like really good things, like in this one it has beans that wasn't clear for me in the beginning. So maybe he's actually good because he's not so hard. But well, I think lots of this thing could be explained to schoolers, the undergraduates, so actually good. Use it like in my work, so played some things. So